Hello everybody. This video is to help us with understanding how to graph tangent functions with a phase shift and a period. So what we're going to first do is review how to graph the tangent function. Just a basic tangent function, um, and then we're going to expand that to, now this tangent function does not have a period change or a phase shift, so it's going to just be a very basic tangent function. And one of the things we want to remind you of is if we were studying the unit circle or we were looking at an angle as it goes around a circle, the angle theta, the tangent ratio can be thought of if you have y equals tan of theta or tan of x. The tangent ratio can be also thought of as being the slope of the terminal side of an angle in standard position. So for example, when I have a 0-degree angle, okay, the slope of this line is 0. So you can see that's horizontal, so the slope here would be 0. But when we get to a 45-degree angle, or pi over 4 radians, we have a slope of 1. And when we go vertical, and we're at pi over 2 radians, or 90 degrees, we have an undefined slope. So some values that we need to know is that when theta is equal to 0, 45, 90, and then, we get past that and we go back to 135 degrees in quadrant 2 or 180 degrees in quadrant 2, that the tangent ratio basically is 0. Then it becomes 1 at 45 because the slope of that terminal side becomes 1. Then it goes to an undefined value. So I'll write undefined or infinity. Then when we get to the other side here, the slope becomes -1. And then at 180, the slope becomes 0. Now, when we plot this, we want you to be aware that wherever it's undefined, we have an asymptote. So I'm going to make this 0. We go through the 0 point. When we get to pi over 2 radians, we are going to be at an undefined slope. And when we get to pi radians, we're back at 0 again. So if we go backwards, where we look at angles that are negative in value, for example, when we go to negative pi over 2, the slope is also infinite in value. And if you can just study that by just looking at, if we have our terminal side, let me just erase that. If our terminal side is pointing down, that's at 270 degrees or negative pi over 2 radians, the slope of that line is also infinite in value. Tangent function basically has this basic parent function, and this repeats itself every pi radians. So, if I were to extend out the axis and make this go out to 3 pi over 2, I would have another asymptote, and the tangent function would proceed as follows. And this repeats itself over and over again. And another note is that the fundamental period of the tangent function is pi radians. If you're in degrees, that's the equivalent of 180 degrees. So using that information, we're going to plot a function that has a change in its period. So what we want you to do is we want you to write out what the amplitude would be, that's 1. What the frequency value would be, that's 2. What the phase angle would be, because there's nothing inside, would be 0. So the fully developed tangent equation would look like this. And the vertical shift is 0. So we really just have a frequency change in this problem. B is equal to 2. And what that means, the frequency changing in this case, is we're going to see the tangent function twice during every fundamental period of pi radians. Well, what we do when we're plotting this is we want to also find a couple other pieces of information. We want to find the real period of the function. The real period of the function based on the b value is equal to pi over b, and in this case is equal to pi over 2. So that's the period of this function. We also want to find the starting point of the tangent function. The starting point is always equal to, by setting the inside of the domain variables or the independent variable area equal to 0, we can find out where that tangent function moves to. So it's equal to negative c over b in this case, because c is equal to 0. It doesn't matter what b is. The starting point is at 0. We also want to find out the ending point. The ending point, it's not really an ending point, it's the end of a full cycle. So the end of a full cycle would equal the starting point plus what the period for that function is. So in this case, we have 0 for the start point plus a period of pi over 2. So we know that our next cycle will begin at pi over 2 radians. Now, if we know that pi over 2 radians, a full cycle will repeat, we know that where to place all of our zeros, because every pi over 2 increment, we're going to be at the origin again. And in between, from looking at the last function, in between each one of our zeros, we have our vertical asymptote. So once you plot your points, you can then plot directly in between your vertical asymptotes. And we're taking advantage of our knowledge of the fundamental graph of tangent to draw these more complicated graphs. So over here at negative pi over 2, I have another 0 because of the periodicity of the function. And, oh, I think I made a mistake. Let me just correct that. I'm just going to move that along. And I think this value is incorrect. So this next 0 would be here, and that'd be at negative pi over 2. Now I can draw in the functions just like I drew before, the tangent functions. And we have what would be a few cycles of the tangent function. In the next problem, we're going to draw a function where it has a frequency change or a period change and a phase shift. So what we're going to do in this case is we're going to do the same exact approach we just had. We're going to write out our amplitude, which was 1, our b value, which is 2, our c value in this case is negative pi, and our d value equals 0. So here we have both a phase shift and a period change. So let's calculate what the new period is. The new period is pi over b, which will equal pi over 2. We have an actual starting point change. It's negative c over b, so the starting point is going to be pi over 2. And we have our endpoint will equal this. The endpoint again is basically where the starting point repeats itself. So this will be equal to pi over 2, the starting point, plus the period, which is pi over 2. And that equals 2 pi over 2, or pi. So let's graph it. So we have our starting point is at pi over 2. So I'm going to make this to be pi over 2. This will be pi. This will be 3 pi over 2. So these points, this is where the function will repeat itself. In between there, we have our asymptotes. And then we draw our function. We also want to label what our asymptotes are at. You can, by visual inspection, see that they're equal to pi over 4, 3 pi over 4, 5 pi over 4, or we have an equation for that also. The left asymptote is always equal to the starting point minus half the period, because the period is the full width of the function. So if you subtract the period divided by 2, you'll get the left starting point, or left asymptote, I should say, and that would be pi over 2 was the starting point minus pi over 4 gives you pi over 4. The right asymptote equation would be the starting point plus the period divided by 2. And that would end up being 3 pi over 4. And as you can see, we had those values from just doing the visual inspection to the graph. Hopefully this video helps you understand how to graph a tangent function and how to graph a tangent function when its period and phase shift change. Remember, the fundamental period of the graph for tangent is always going to be pi for the basic tangent function. And this will be altered by if you change your B value. So anyway, or your frequency value. Hope this video helps, and I look forward to hearing your comments in class, and have a good day.